today what we're going to do is we're going to do an introduction into kinetics. So what is kinetics? Well, it's essentially determining how fast reactions go. So let's take a look at the notes here, and let me remind you of a couple things that we talked about before. Last unit we talked about something being spontaneous or non-spontaneous, and what that meant was the reaction either went or it did not go. And that's due to Gibbs free energy. Now, we're not going to talk about cell potential because that is a unit that's not going to be covered right now. But we are going to take a look at how people think that reactions go. And we're going to kind of go like we always did, from what was kind of the worst ideas to some of the better ideas. So the first model that we thought was a really good model was called the collision model. Now, that's based on this really simple idea, and the simple idea is that if you have one molecule, let's call that molecule A, and it bangs into another molecule, let's call that molecule B, when they hit into each other, that's where they hit, when they hit into each other, they react. And so they form new stuff. So if you have A and B, they're going to form something new. I don't know, maybe AB. But when they started studying the rates of reactions and they compared it to the collisions, they found that the vast majority of collisions did not produce reaction. In fact, that we see that, however, that not every collision between molecules create process. In fact, the vast majority do not. Now, why is that? Well, there's two basic reasons why every collision is not effective. So first of all, we're going to talk about how molecules are oriented. So if we take a look at the reaction below here, Br reacting with Hi, not only do molecules have to hit each other, but they have to hit each other in the right way. This is known as the steric factor. It's a weird word, steric factor. So if we took a look at this right here, we would very quickly see, I'm going to go over here on my other screen, go back here to you, sorry. If we were to take a look at Br, right, if Br comes in contact, and let's say I is on this side and H is right here, the Br wants to interact with the H. So if it hits into the I, nothing is going to happen. But if it happens to contact it in the right orientation, where the H is on this side, which is what it wants to interact with, let's just say this right here, then it will react, and you'll end up with HBr, and the A gets kicked off. Does that kind of make sense? So the biggest thing is you have to orient in the correct way, or else the reactions won't happen. The second is activation energy. Now, what is activation energy? Well, it's the amount of energy required to make a reaction go. Now, if you think about it, we talked about this last unit about how molecules had to first be broken apart. Their bonds had to be broken on the reactant side and then reformed on the product side. And that requires a lot of kinetic energy. So if two particles are screaming into each other, the amount of energy they have to have, the amount of kinetic energy they have to have, has to be equal then or greater than the activation energy, or else the reaction won't go. So we can say this, the amount of energy called activation is needed for the reaction to go. So the kinetic energy of the reactants colliding must be greater than the activation order for this to occur. And the reactants must collide in the correct orientation. Now, just to be clear again, two things have to happen. You have to collide in the right way and with enough energy in order to be able to produce products. That kind of makes sense? Now, what helps a reactant go? So there's a few things that will help a reactant go, and you probably have guessed these already, but let's just jot them in here anyway. Let's use a different pen because the blue has I've grown weary of the blue. Let's try this. Let's try the purpley. So higher temperature. So we probably know this, but let's go higher T for temperature. When molecules move around more quickly, they end up having greater kinetic energy. And if you have a higher concentration, more particles, I'm going to do this for concentration. Higher concentration of reactants increase the rate. So two things that will cause a reaction to go more quickly are greater temperature, an increase in temperature, and an increase in concentration. So if you have a lower concentration, as this delightful diagram shows, you're not going to have as many collisions, lower collisions, right? And if you have lower collisions, there's not as many chances for you to react. And then, so obviously higher concentrations means more collisions. But also, if you're moving faster, you typically have a greater kinetic energy. And that greater kinetic energy provides more energy, and it's more likely that you're going to be able to break all the bonds that you have to break in order to form something new. Bottom line is this. Reactions can occur just by molecules banging into each other. However, most of the time when molecules hit, nothing happens due to high activation energies and steric factors. Okay, so where does that leave us then exactly? Well, let's take a look here. We have a new model that we're going to look at, and that new model is called the transition state model. So let's go over here and let's scroll down. Of course, I have some issues with my screen. There we go. So it's called the transition state model. Let's drop that in here at the very top. Transition state model. So there was issues with the collision model, just two things hitting into each other, because they discovered that when you actually took a look at the activation energies that were required, they were much lower than the energy needed to break all the chemical bonds. So this new model says, hey, instead of breaking all of the bonds first and then reforming all the new bonds, what if we do them kind of simultaneously? And they came up with the idea of an activated complex. Activated complex. And an activated complex, we sometimes know it as a transition state. So activated complex or transition state. And here's the idea. And I'm going to give you an example. So here you have a C triple bonded to an O, and you have NO2, right? And so normally what you'd think we'd do is we'd have to break all these bonds and break these bonds right here, and then reform new bonds. And that amount of energy is significantly different than the energy we actually recorded as activation energy. And what they discovered, and what they now think occurs, is that these two things right here, the carbon and the oxygen, they're going to try and form with each other, right? But in order for that to happen, what ends up happening simultaneously as this bond starts to form, as this bond here starts to break. So this activated complex can sometimes only exist for like thousandths of a second, and so it's really hard to study them. But we believe that that's the new model of how reactions work, and how overall. Let me put a pen right here. Trying to scroll down, and I'm using two screens. Sorry. Let's take another look at example here, and this kind of is very similar to the previous one here. So Cl comes along on the side that's opposite the Br. Comes in over here, and it starts to form. Do you see right here? It starts to form the bond with the carbon in the middle. And simultaneously, this bond right here starts to break. And the end result is that the Cl takes its place. So this is the activated complex. Now, how does that look on a graph? Well, this is how it looks on a graph. This right here is the activation energy, and it shows right here on the graph. This EA is how I wrote it, right? That's the amount of energy that's actually required. And so when we have an activated complex, and it occurs at the peak here, the amount of energy that's required for one of these things right here. So like for one of these, like this right here, where one thing is starting to form, the other thing is starting to break, that's a lot more energy efficient than actually breaking this bond first and then reforming the bond second. And so that gives us a lower curve. If not, the math that we thought was going to happen was going to be something like crazy up here, and instead it's a lot lower. And again, if you take a look at this, you'll see how this is a change in enthalpy is negative. So this is an exothermic reaction, right? But just be aware that this is how we now view that an atom or that a reaction works. We think that the reactants start to break their bonds while the products start to form their bonds, and in the end we end up with this activated complex. Now, the two main ways that people thought that reactions worked were the collision model and the transition state model, but now we're going to go to figuring out how fast this goes, and that's going to take us to video 2. Hopefully this has made sense. I'll see you in the next video.